Let's go over flow and diffusion simulations. The core idea of generative modeling is to learn a transformation from a simple, easy-to-sample probability distribution. These transformations are achieved by simulating a differential equation over a time interval. P data represents the data distribution, the underlying probability of all possible valid data points. In our 2D simulation, the data points are simple x and y coordinates. The shape of P data directly determines the vector field. The field's purpose is to push random points from the center towards the areas where data is dense. For a star, the field will point outwards along the arms of the star. For a circle, the vector field will point radially outwards. For the checkerboard, the field is complex, pushing points towards multiple distinct clusters. The learned vector field is essentially a compressed map of the data distribution's geometry. Here we show some simple flow versus diffusion simulations. The goal is to learn a deterministic transformation from noise to data. A neural network learns a vector field that defines the exact path for each particle, governed by an ordinary differential equation, ODE. The process operates on the entire image at once. An image is not treated as a collection of independent pixels, but as a single, high-dimensional vector z. If an image is 128 times 128 pixels with 3 color channels, RGB, it's represented as a single vector, R, which is 49,152 dimensions. The network's architecture, like a U-net, is designed to understand the spatial relationships between pixels. It doesn't just learn this pixel should be red, but rather, given the entire noisy image, the collective velocity vector for all 49,152 values should be this, in order to make the image slightly less noisy and more coherent. With flow matching, the goal is to learn a deterministic transformation from noise to data. A neural network learns a vector field that defines the exact path for each particle, governed by an ordinary differential equation. An example workflow would be as follows. We pick a data point z, a noise sample epsilon, and a random time t to create one training example. Form a noisy sample by interpolating the variables and find a point on the path between the noise and data point. We then calculate the correct velocity vector by the analytical formula for the conditional vector field. Then the network predicts a velocity. The loss is the mean squared error between the prediction and the ground truth. The loss is used to update the network. Now let's move to diffusion and score matching, the SDE approach. The goal is to learn a stochastic transformation. Particles are guided by a vector field, but also continuously jostled by random noise. This process is governed by a stochastic differential equation. The setup is the same, and the noisy sample is created in the same way. The difference is stochastic differential equations need a score function, which points towards areas of higher probability. The tractable conditional score is calculated. Then the score network predicts the score, and loss is calculated via the ground truth score. Be sure to check out other tutorials, overviews, and even download the code for these lessons on the GitHub in the description.